we looked into some properties of the action and how to derive the general equations of motion from the action principle. So we have properties of the action and the Lagrangian. And there are a few simple properties that typically help us constrain the form of the action and the Lagrangian. And some of them are really simple. Being, for example, that S is proportional to 1 in the sense that it's dimensionless. If we set h bar equals c equals 1. And from the action being dimensionless, we can of course conclude that the Lagrangian has dimensions mass to the fourth power or 1 over length to the fourth power. In general, so that's one property that helps us check what are the appropriate parameters we have in front of a certain combination of fields. We determine the dimensions of the fields, and then we say, oh, a derivative counts one mass dimension, a field counts so and so many, and then at the end, if we add all these things together, we have to end up with mass to the fourth power. And the mass dimension of the field itself, we can read off from the kinetic term, just so that it exactly matches, so that the kinetic term matches the appropriate dimension for the Lagrangian density or the action. The other thing that helps us constrain and simplify the action is S is invariant under all symmetries of the system. And that allows us to say, oh, I identify all the symmetries of my system. Maybe it's rotationally invariant, it's Lorentz invariant. It has some internal symmetries, like I can flip or exchange two fields inside without changing the system. So all kinds of symmetries. And S should be invariant. And today we'll learn more what to conclude from an action that is invariant under a symmetry, or what it means physically for a system to have a symmetry. And in particular, if we have Lorentz symmetry, not all systems have Lorentz symmetry, but if Lorentz symmetry is a good symmetry, then the Lagrange density should be a Lorentz scalar. And that means no indices, very roughly speaking. So that allows us to constrain and to simplify our action to a large degree. And then, of course, we obtain the equations of motion by taking the Hamiltonian principle. And we can do this in a rather general fashion by following the steps we did yesterday. And then we get the Euler-Lagrange equations. And here, of course, this phi can be any fields, any number of fields. So if you want, you can give it an index and an index here, and then you can do all kinds of fields. This can be a scalar field. This can be a component of a vector field. That can be a component of a spinor field. Can be all kinds of things. This Euler-Lagrange equation remains more or less the same. OK, so now let us proceed what to actually do, make physical use of symmetries. And this is really one of the most fundamental connections in physics, the connection between symmetries and conserved quantities. And that's the Noether theorem. You may have encountered it already in classical mechanics, but it also holds in field theory. And this connection even holds to a large degree in quantum field theory. So symmetries, so just to give us conserved quantities. That's the fundamental statement. And now, today, we want to make it a little bit more precise. OK, so I'll again do it very schematically. I'll basically write it as if there were only one field. But you can easily generalize to any number of fields you like. So let us assume a field transformation. And this field transformation takes our field phi into a new field phi prime, which is equal phi of x plus alpha delta phi of x. And for simplicity, I assume that this is infinitesimal. And this is infinitesimal also requires something of the symmetry. If we can take this infinitesimal, that of course simplifies our calculation in the following, but this also requires that we have a continuous symmetry, one that changes smoothly. It's not something where we have only two states, so to speak, between which we flip, but it's rather something like a rotation symmetry which we can change continuously. So needs continuous symmetry. Okay. Now, a symmetry is one, and that's now we can simply turn it around. Our definition or our idea of a symmetry, we turn it around and say a symmetry is a field transformation that leaves the action invariant. Meaning delta S is equal to 0, or more precisely, i.e. S of phi is equal S of phi prime. So that is how we define a symmetry. We actually define a symmetry as being a field transformation that leaves the action invariant. Okay, so we have always talked about the action and the Lagrangian density. So the question is, what does this requirement mean for the Lagrangian density? Well, the Lagrangian density, just to remember, is the integral over the Lagrangian density is the action. So you can immediately guess that if you leave L unchanged, the Lagrangian density unchanged, then the action is also unchanged. So if the Lagrangian density is unchanged and invariant under the symmetry, so is the action. But this is not the most general case. There is one thing we can do, and which we can add to the Lagrangian density, which still leaves the action invariant. And basically S invariant works if we take L of phi. If we take it to the same, so if the Lagrange density is also invariant, then of course it's a symmetry. But we can add one thing which doesn't affect the integral, and that's the total derivative. Because the total derivative, if all the boundary terms drop nicely to infinity, to 0 at infinity, doesn't change the integral. So we can add alpha times d mu k mu, where this is the total derivative of some function over here, or some current function, so to speak, if you want here. So any change by a total derivative, and this is a total derivative, doesn't change the integral. Okay, can you maybe so left? Thanks. Ah, okay. Very good. That was quick. Okay. So a total derivative does not contribute to the integral. Okay, so now that we know how our Lagrangian changes under the transformation, we can compare the change in the Lagrangian that we are allowed to have if the thing is supposed to be a symmetry to the one we can directly obtain by plugging in the field transformation. So we can directly plug in the field transformation and calculate the change in the Lagrangian. Then we compare left-hand side to what is allowed for it to be a symmetry. So the change in L. And how do we do that? Well, we call the change in L delta alpha of L. And, well, we simply calculate it by plugging in our field transformation and using the fact that we have made a very small one. What do we get? Well, we get the derivative with respect to phi. We simply follow the chain rule, and then alpha times delta phi, because that's the variation with respect to phi, and that's the change in phi. So it's simply taking the chain rule, basically. So, and of course, the Lagrangian also depends, as usual, on the derivatives of phi. And then, of course, we have to take the internal derivative alpha delta phi. Okay. This term looks already quite good. Here, again, we have this kind of situation where we have a derivative on something which is rather unspecified. So what do we want to do? Well, we can basically add a term to make this a total derivative of the whole thing. So we keep and if you allow me, I'll erase that and factor alpha out right from the beginning. Put alpha outside here. So I say dl by d phi delta phi. And now let me add a total derivative. D mu, big thing, dl d mu phi. I cannot immediately throw away total derivatives because I don't integrate. I'm calculating the change in the Lagrangian density. So I have no integral, so I cannot throw away total derivatives. But it nevertheless may be convenient to actually introduce it. So this term over here, if you apply the derivative to the delta phi, gives us exactly this term over here. But it also gives us an additional term where the derivative acts on this term over here. And so we have overcounted a little bit, so we have to subtract the term where this derivative acts on on this term over here, multiplied by delta phi. Now, if we look at it, this term and this term together are simply our equation of motion multiplied by delta phi. So these terms together equal 0 by the equation of motion. So this is just the dl by d phi minus d mu dl by d mu phi. That's just the equation of motion, or the Euler-Lagrange equation. So our change in the Lagrangian, after applying the equation of motion, is simply this term d mu dl d mu phi delta phi. So that's our left-hand side. So that's our change in the Lagrangian density, which we obtained directly by plugging in our field transformation. And this over here is our right-hand side, which is a change which we are allowed to have. That means clear the middle. This means delta alpha of L must be equal, and the change in the Lagrangian density is, of course, just this, because the rest is completely invariant. It's just alpha d mu k mu. Okay, so we have at the end, so this is, we can now plug in explicitly our term over here. So we have alpha d mu dl by d mu phi delta phi is equal alpha d mu k mu. Okay. Alpha was infinitesimal, but otherwise completely arbitrary. So we can simply erase it. And then we can nicely put everything on one side to obtain d mu dl by d mu phi delta phi minus k mu equal 0. So this whole thing here is something we can calculate from our symmetry. It's fixed for a given symmetry. And the interesting thing is now that we have a quantity here, which is calculated from the symmetry, and from which we can take a derivative which is equal to 0, or more precisely, on which we can act with a divergence, such that the whole thing is 0. So we can call this, if we want, a current. And then what we have here, because these are two parts of a current, so if we combine them, we have a nice current here. So we have a current J, which is conserved. d mu j mu is the equation for a conserved current. Okay. So this is already our Noether theorem. A conserved current is something really physical. Just think about it. In electromagnetism, this is truly the electromagnetic current. It's the combination of charge and the current vector, and that is a conserved quantity. Basically, it means that whenever you cannot create charges. And this connection to the charge we'll see more clearly in a second. But let me first summarize this. So this is really already the Noether theorem. For every continuous global symmetry, and I should explain the word global. Global means that this alpha here, this parameter, does not depend on space. So we do the same transformation to the fields everywhere in space. For every continuous symmetry, phi goes to phi plus alpha delta phi. We have a current, J mu, dL by d mu phi delta phi minus k mu, which is conserved. i.e., and this is an equation you know very well from electrodynamics. Now, what can we do with our current? And that makes the connection to conserved quantities more explicit. From each conserved current, we can actually find that we have a conserved quantity. So let us see this briefly. So from a conserved current, we find a conserved charge. And how do we do that? The conserved charge, Q, we want to define as the integral over all of space, J0. And that this makes sense, you can think back by comparing to electrodynamics. In electrodynamics, the conserved current is the charge density and the current density. So the zero component of the electromagnetic current is the charge density. And of course, if you integrate over the charge density over all of space, then you have the total charge. And the total charge is something which is conserved in electrodynamics. But now let us convince ourselves that this quantity is actually conserved if J is this appropriate conserved current. Make it like this. How do we do that? Well, let's simply take the time derivative of this charge over here. So this is 3x. And as usual, as a physicist, I'm simply pulling through this time derivative and have it act on the zeroth component of the current. OK. Now, this we can write and complicate a little bit. So we have d0, j0 plus di, ji. and I'm taking lower and upper indices to account for appropriate minus signs from the Minkowski matrix. But the whole point is I simply add dij minus dija. And, well, if I do that, this together, taking upper and lower indices appropriately, is just d mu j mu. So that is our divergence of the current. And therefore, if our current is conserved, this is equal to 0. So in total, we have something like equal d3x minus di ji. But again, this over here is now a total space divergence, which I integrate over all of space. And if all the fields drop sufficiently fast at infinity, so if our charge distribution, so to speak, is localized, then this one over here is 0. Integrals over total derivatives, if the fields drop at infinity, are 0. So using this, we have already shown that this is actually truly a conserved charge. So this actually is our desired conserved charge. So our Noether theorem gives us, we have a symmetry. From the symmetry, we obtain a conserved current, meaning a current which has 0 divergence. And from this conserved current, we then can find a conserved quantity or a conserved charge. And the point is really, in classical electrodynamics, this really is the electromagnetic charge. Of course, and that should be noted, there can be any kind of constant in here, because, well, our current is still conserved if I put a constant over here. So if I multiply by a constant, the current is still conserved. So any conserved current is only defined up to a multiplicative constant. Okay. So this is the middle board here. Let us do an example. Let us take an action S of phi, which only contains one field. And this is just a scalar field, but a complex scalar field. So it's d mu phi star, d mu phi minus m squared phi star phi. From yesterday, you recognize we have the structure kinetic energy minus potential energy. So here we have a kinetic term. Here we have a potential term. And we'll later see that this is actually the action for a free particle in relativistic quantum mechanics. Okay, or a free, more precisely, charged particle in relativistic quantum mechanics. Now, here we have phi star phi, and here we have phi star phi. So we can already guess that this action has a symmetry. And the symmetry is that phi goes to exponential times I alpha. So we can multiply it by a complex phase times phi. And if we take alpha to be very, very small, decimal, then this is phi plus I alpha of phi. And similarly, of course, we can conclude that the transformation for phi star is exponential minus I alpha phi star equal phi star minus I alpha phi star. Okay. If we plug it in, we can easily check this is a symmetry. And by plugging it in, we also immediately find that the Lagrangian density, so this is the Lagrangian density here, doesn't change at all. So delta L is actually itself is already 0. That means that K mu is equal to 0. Okay. Now, that's not good. Let me actually continue on this board. So we already know this bit of our conserved current is 0. And now we have to explicitly calculate this bit of our conserved current. And actually, this can also serve as a practice how it works for more than one field. Because we actually have more than one field because we have phi and phi star. You can say phi and phi star are not really independent fields. But if you want, you can write everything in terms of real fields. And then you have the real component and the imaginary component. So you have, again, two real fields. So it's quite useful, typically, to treat phi and phi star as independent variables when doing derivatives and so on in field theory. And it's completely equivalent to splitting it in a real and an imaginary part and then doing all the derivatives. So treating these two as independent works just as well. So let me kind of improve this part over here by simply putting in an index I. So basically, we are summing now over all possible changes in this field, or all direction, or the whole direction in field space. So this becomes kind of a scalar product, if you want. And now we have two changes, two fields, so we can call this phi 1 and phi 2, which have, one has a plus change and one has a minus change. So our conserved current is now therefore J mu is equal dl by d mu phi. And, well, what is, and now we have to multiply by delta phi, divided by alpha, so to speak. We drop out the alpha. So this is times I times phi, because that's our change, dropping out the alpha. I times phi minus, plus dl by d mu phi star. And now we have minus I phi star over here. And now we can simply evaluate these derivatives. This one over here, so we can factor out an overall I. We have a derivative here, so this is d mu phi star, this derivative times phi minus d mu phi times phi star. And this is our conserved current. This one over here. Okay, now we can, just as a check, convince ourselves what is this current actually conserved? We can explicitly calculate that this current is conserved. So we check d mu, j mu. And what we find is, well, we can always factor out this factor of I. Now, we act with the lower d mu over here, the first term. So we have d mu phi star times phi plus d mu phi star. Sorry, that should be an upper index. Oops. D mu phi star d mu phi, and then minus d mu phi phi star minus d mu phi star. Okay, so what can we do? Well, this term over here and this term over here are identical and of opposite signs, so this and this cancels. This here is box phi star. And box phi star is equal to 0 by the equations of motion. And I would suggest, I think it's also one of the exercises, that you derive the equations of motion for this field, and you'll find that this is one of the equations of motion, and that this is 0, again, is because it's box phi. And this is simply the equation of motion. Okay, so we've obtained our Noether, or our conserved current, directly from the Noether theorem, but we can also directly check that this current is truly conserved. Yes?
I don't think you're going to get box squared phi star is 0, but you'll get box squared phi star is m squared phi star.
Oh, sorry, yeah. Yeah, sorry. I was putting it to be massless. You're absolutely right. I shouldn't. So that is plus or minus m squared phi star. You're absolutely right. I've in my mind set plus minus m squared phi. Very exactly. Very good. Now I've simplified a little bit too much. So it's phi star phi, which then cancels exactly. Sorry about that. I was oversimplifying a little bit. Okay. You also had a...
I didn't understand the first line.
The first line?
Yes.
Um,
when you're applying the star, P star, sorry.
So here, this is just this term.
Yes.
Now, our change in the field over here, that's alpha times delta phi. And this is alpha times delta phi star in our derivation. And, well, that means delta phi is I times phi. Delta phi star is minus I times phi star. And now I simply use the formula we have derived for the Euler, for the Noether theorem. Okay? And what I haven't shown in detail, but which you can do by simply taking a little bit care of the indices, is that you actually have to sum over all fields which change under the symmetry transformation. And under this symmetry transformation, phi and phi star change, and we treat them as independent fields. Okay. So that's one example. Go back. Oops. missing something. Ah, no. Here we are. Someone uncleared. Very good. Let me actually also clear this one. Very good. Okay. So this was a straightforward example where we had a so-called internal symmetry. The symmetry doesn't act on any of the Lorentz structure, but it acts by changing the fields a little bit. So it's basically changing the field by a phase. But we can also have so-called space-time symmetries, which really change and basically which also act on the space-time. And the prime example, or maybe also in a way the only example, is Lorentz symmetry. And just as an example, I'll not do the full Lorentz symmetry. I'll go for translations. And actually, translations, I shouldn't call it Lorentz symmetry. I should call it Poincaré symmetry. Because Lorentz symmetry, if you take it very strictly, is just the rotations and the boosts, whereas Poincaré symmetry contains the spatial and time translations as well. Okay, so let us do a translation. X mu goes to x mu minus a mu. So we translate by an infinitesimal vector. So we have an infinitesimal vector. And we should note that it's a vector. It's a vector. So we can do different types of translations. We can go in the one direction. We can go in the two direction. We can go in the time direction. So we actually have more than one possible transformation. And of course, in a way, also symmetry. We have translations in space directions. We have translations in time directions. Okay. Now, we want now to calculate our changes in the fields and also our changes in the Lagrangian. How do we get the changes in the fields? Well, let's do it for a scalar field. And now I should really say this is a scalar field. So we have done our translation. After our translation, we have moved our point to x minus a. So our new point, our field, should now be evaluated at x plus a. And if our translation is infinitesimal, we can basically expand around the point x, simply go to the first order in the Taylor expansion, and transform it like this. So this is the transformation property for a scalar field under translations along the vector a mu. And the good thing now is this tells us also how to transform the Lagrangian density, because it's a scalar too. And therefore we have L goes to L plus A mu d mu L. And we can write this in a bit of a strange manner, which is more useful because we want to put it into the form of this total derivative. If you juggle the indices a little bit around and add a delta, you find that this is actually A nu times d mu delta mu nu on L. So this now has the form of a conserved, or not a conserved, a total derivative k mu, but it's not just one total derivative, it's a whole bunch of them counted by an index nu and then added together in the direction of this vector. And of course, we have our total derivative. So we have a whole bunch of k's over here for each direction in which we do a translation. Look here, this index of the current, or not the current, I shouldn't say the current, the conserved, the total divergence, the k that is added as a total divergence has an index nu which corresponds to the direction in which we take our translation. So for every direction, for the time direction, for the space direction, we get one of these total divergence terms. So already erased that. So for every nu, we can now use our Noether's theorem with k mu mu. And this is the mu, this is the k mu, but now it really has itself an index nu. Therefore, we now get not just one current, but for each nu, we get a current. And, well, since we now have a two-index object, and you can already see from the fact that this is a proper Lorentz index, we'll actually get an object with proper Lorentz indices. We'll give this a new name. We call the current T mu, but it comes with an index nu because we can get a current for each conserved, for each direction of translation. And this current is given by our formula for the conserved current from the Noether theorem. So we take the derivative with respect to d mu phi, and then we plug in our change of the scalar field, which is actually d nu phi, because here we have our derivative. And then we have to add our k mu, and our k mu we can explicitly read off to be delta mu nu times the Lagrangian itself. That's what's here in the brackets. So we have times L delta mu nu. And the property is, the conserved property is d mu. It has to act on the current index, so to speak. So it acts on this. But it's a whole bunch of conserved currents. So we have a whole bunch of conservation equations. So we have in total 4 conservation equations. And from my notation, you may already know what that is. This has a very special name because this is the energy momentum tensor. Or stress energy tensor. Okay. So what have we now connected? We have connected time and space translations to energy momentum conservation, because this becomes exactly energy and momentum conservation. Yeah. Okay. Let me erase this one and come to the end. Okay. Just as an exercise, and to make this a little bit more explicit, here's this, yeah. One can also do the same steps we have done here for a scalar field. You can follow for a vector field, or more precisely for the electromagnetic field, and therefore we apply the same to the electromagnetic field with 1 over 4 minus 1 over 4 f mu nu, f mu nu. Of course, in this case, you have to do the appropriate sum over the fields. And what you obtain, I'm just giving you the results, is electromagnetic by d mu a rho d mu a rho minus g mu nu L electromagnetic. Did I use G or eta? I think I used eta. Sorry about that. Eta mu nu. Okay, and the bottom line is you can evaluate this, and you can in particular determine certain interesting combinations of these indices. You can find that this is actually 1/2 E squared plus B squared plus the divergence of phi times E, and T0I is equal to E vector cross B vector times I plus AI times the electric field. And AI is the vector potential. So you already notice, looking at this, the 0,0 component of this energy momentum tensor, actually it justifies its name energy, because if you look at it closely, this is the energy density in electromagnetism. And this over here, the T0I component, or a big part of it, is actually the Poynting vector, which is associated to energy flow or momentum flow. And accordingly, you get the conserved quantities. T00 d3x. And what you find, and that's the nice feature and something that you maybe should check for yourself, is actually that this is 1/2 space integral. And this is just e squared plus b squared. This total derivative does not contribute to the total integral. So this is truly the energy of the field. And similarly, T0I is equal d3x. The strange term over here drops again, doesn't contribute, E cross B index I. And this is speed of light times the field momentum. So the electromagnetic field, so an electromagnetic field configuration carries a momentum, which is given first in terms of this energy momentum tensor, but then you can say it's simply the integral over the Poynting vector. If you do the same thing for the rotations and the boosts, you get the analog of angular momentum conservation and an appropriate conserved current. Okay, so let's wrap it up for today. Oops. So the important points really are that the Noether theorem connects symmetry to a conserved current, which then in turn leads to a conserved charge, which is simply given, so it connects to a conserved current G mu, d mu, j mu equals 0, and it gives us a conserved charge, which is a space integral, and it's really space, it's not space-time, of the zero component of this current, such that this time derivative is equal to 0. And that's what it means to be a conserved charge. And this has really wide applications. You can determine conserved quantities like the charge in electrodynamics from its internal symmetry, but you also get energy momentum conservation by looking at the Lorentz symmetry and the translations more precisely. So the translations in space and time give you energy momentum conservation. So say translations energy momentum conservation. So this is an example, if you want. Okay, so yeah, that was all for the week even. Yeah, maybe you have another lecture tomorrow, but we'll see each other together on Monday. Okay, doke.
What was the motivation to bring this this is connected.
I have erased it, so let me.
Sorry to ask.
No. It's always good to ask. By the way, I'm not a professor, so I'm just a lowly lecturer. But I should probably.